Naga, Rajesh, do you have any kind of software familiarity with HISIS? I think Naga will be.
Yeah, not clear your voice.
Do you have any familiarity with HISIS software?
HISIS. Yeah, I have seen HISIS software. I work a little bit on HISIS. Yes.
Did you work with it before?
Work with.
Work with it.
Yeah, a little bit. We have some simulator software, so HISIS is there. So we know how it looks like and all. Yeah,
Okay.
but not deep.
Not. I don't want to deep. I want to just hit and balance from software, so we can work with our engineering disciplines in our company. We will make a company in the course. Raja,
Yeah, hi.
do you know how to read BNID, right?
I know a bit, not that familiar, but slowly just getting into that.
Okay. You have a white paper and pencil. You will draw a lot
Yeah,
today.
it's with me. I have.
Okay.
Shahid, you're from Abu Dhabi or
Hmm?
you're from Abu Dhabi?
Me? No.
Yeah.
I've been in Abu Dhabi for like 4 years.
It,
But now I am in Egypt.
from Egypt. Okay, okay.
Hi, Mr. Faiz. Welcome on board. Hello, Mr. Faiz. Are you there?
I think his mic is off.
Yeah.
Yeah, I think we can start now. I already tried calling the other participant, but he's not picking up my call. I already tried to message him as well. Maybe he will catch up in a bit. So yeah, good morning everyone. So thank you for participating in today's process design training. So I believe before we start, could you please just introduce yourself one by one and like a short background of what you do for the information of Dr. Saeed. So let's start with Mr. Satya, Naga Satya.
Yes. My introduction.
Yes, please.
Okay. My name is Satya. I'm working in Sohar, Oman. So I'm in production department. Would like to know about some process fundamentals just again one more time. So that's why I'm participating. Yeah.
Okay.
Which,
Thank you, Mr. Satya.
which unit you are working in?
Which?
Unit you are working in?
Yeah, I'm working in Sohar.
Which unit? Unit operation.
Unit. It's a petrochemical company.
Ah, perfect. Okay.
Okay. And then let's move to Mr. Raja.
Yeah, hi. Good morning to all. So as stated, I'm Rajesh Shekhar. I'm from Oman too. So I'm working in an training and consultancy company at Oman. So I'm working as a senior HSC instructor, and I'm doing a master's in process safety. First year has been completed, and now I'm into the second year. So I need to know some more details about process. So that's why I'm into the course.
Thank you, Mr. Raja.
You-
And then we have Mr. Faiz. Yeah, Mr. Faiz.
Yes, good morning all. My name is
Good
Faiz.
morning.
I am working as a process engineer in Saudi Arabia.
Thank you, Mr. Faiz. And today our trainer would be Dr. Said Amar. Dr. Said, I believe it's better for you to introduce yourself to the participants.
Okay. My name is Said Ammar. I have more like 22 years experience. I'm coming from operation background. I work in engineering like since 2013. I work as in process safety also like 2012. I have a PhD in petroleum economics. I have a master degree in LPG recovery. I am a charter engineer since 2016. I'm the first professional safety engineer accredited from ICME. I just get my accreditation last June. What else? I am a HAZOP team leader accredited from TUV and ICME. As a functional safety engineer and all of this. Any question for anyone? Hello?
Mr. Satya, you messaged something?
Any question
Yeah,
for
yeah,
anyone? Yes, tell me.
You have any other speaker you can speak? Modulation is a little bit different. Sometimes it's coming high, sometimes it's coming low. So standard ear phone plus this.
Is it good now?
Oh, maybe you can talk, then I can see that. So we
Okay.
have to listen very clearly to your voice, then only I'm understanding.
Just if there any problem with the internet, any problem with my voice, just raise your hand, say anything, I repeat it again.
I think you need to increase a bit the volume for Said, if you can.
My volume?
Yes, yeah.
Okay, it is 7 a.m. here.
Okay.
Okay. Mr. Faiz. Mr. Faiz.
Yes, please.
Yes, tell me a little bit about your process safety or process work.
For professional, how currently assigned to project support as a
I don't get anything.
I used to work as a process engineer supporting various unit operation. Now I'm working as a process to project, mega project.
Okay. You got the operation request. Please, we have a problem and we need to solve it, right?
Yes, that was most of my career, but last 2 years I'm working to support a project.
What was your last project?
That is a petrochemical project. We cannot release information about the name of the project because it's not yet approved.
Perfect.
But
Perfect.
I'm working to support the feed stage of the project.
You're totally comfortable with this. That's what I'm searching for. The feed stage. Okay, perfect for me. Can everyone see this process plant engineering activity model?
Can you zoom in a little bit?
No, I will zoom it, but you can't see it.
Yeah, we can see. Yes, definitely.
Okay, you see the link I put it in the chat for Drive, Google Drive.
Yes, I downloaded them too.
Okay, Faiz, please download this link. Faiz. Okay. What we have in the link is, let me share the link with you all. What we have with the link is my last project I delivered. It's called First Core ABC, and the materials for the course, and the HYSYS course materials also, and the standard for the PMID, which I will start today. This Google Drive will be updated every week, updated by your work, my uploads, which I will do for the course. Okay, let's start our Naga,
Yes.
tell me what your process engineering do.
What is the process engineers?
Yes. What your
Yeah.
process engineer in your site doing actually?
Process engineers, they are the process custodians. They will check the plant conditions and operating conditions. Check with respect to design, operating the plant.
Okay. What else?
They can design also, process engineers.
Perfect. If you have a problem with the operation and you invite your process engineer, please, we have a problem in our plant and we can't, the flow is not, there's always a high level in the separator, for example. There's always, this pump always suffer from a cavitation problem. This compressor is always hunting. What the process engineer should start with? This is a question for everyone. I want your thoughts. I want the way you are thinking, that we can follow on this way all the course.
Process engineer, by looking into the process drawing, you should be able to identify the reason for the low flow or high flow. Point out the exact area where there is a defect, either on the system or any human error.
How can he do this? What he
While
yes.
looking into the process flow diagram.
Perfect. One. What else?
And if any safety studies has been conducted, like HAZOP, so that can be also used to see to find the hazards, the deviations?
Hazard will not be affected in solution the problem, operation problem, special like Naga. He will not be able to rely on the hazard to solve the problem.
Okay,
But
okay.
when you buy a new car, it's coming with a new manual, right?
Yeah, manual, right?
Yes. Mr. Naga always have his operation manual. Any operation engineer has the operation manual. This operation manual always consists of all the process activity being done during the project is summarized in the operation manual. How does this come from? What we are going to produce, the process flow diagram, the piping and instrumentation diagram, we are going to generate it by our hand. Then we are going to learn how to size the hydraulic, how we design a separator, how we are using HISIS to design a pump, a compressor. Then we will have the pressure safety valve and depressurization and the flaring system. When we are asking for all this equipment, all this list of equipment, we must have the process flow diagram. The first key is to understand the process flow diagram, is to generate the process flow diagram. When we are going to make a typical gas oil separation nodal compression station for this course, if Naga call me for a problem in the plant, I will start asking him a lot of questions about the process conditions and the operating condition and the boundary limit. Why this happened? What circumstances happened? This upset in the plant. To understand the process engineering or the process design, you have to understand the mechanical design diagrams. The mechanical design diagrams is very important for us. Why? To understand the operating and the mechanical design pressures and temperatures. Why? Once we making a new plant or we have an operation upset, we need to understand the design conditions and understand and gather the operating conditions. How this will be happen without having the mechanical design diagrams? Why we need the mechanical design diagrams? Why it is important for us? Because if you're working in engineering company or you're working in operation, you need to understand the connection between the mechanical engineer and the process engineer. Why? In a normal engineering firm, small sized, you as a process engineer, you will lead all the activity from making the PFD, making the P&ID, and get the input from the mechanical discipline and instrumentation discipline to be installed on the P&ID and even the PFD. So that's why we need to understand mechanical design diagrams. What's the meaning of mechanical design diagram? Is a key design document for the process engineer to establish the mechanical design pressure and mechanical design temperature for equipment and piping. If anyone in the participant, anyone have any problem with understand anything from what I'm saying or have any problem with the voice internet he just need to raise his hand and ask me to repeat it again. Okay? Okay? Hello?
Okay.
Finally. Sound from the gut. Thank you, Raja. Naga, are you with us?
Yeah, it's okay. Yes.
Okay, perfect. Let's continue. If we are instructing or making any equipment, we need to understand the mechanical design diagrams. Why? To prepare an overview of mechanical design condition and piping material specification of a plant. Are we going to make a piping specification? Yes. Is it important for us? Yes. Why? To view the mechanical integrity and safety devices of a plant. I don't get it. Why we are going as a process engineer to make the specs for the mechanical design diagrams? Because if we want to make sure that the mechanical integrity of the equipment, of our plant equipment, we need to make sure that it is rating on the correct method and the operating pressure, operating temperature is within the design envelope of the facilities. Design data which we are using and we are going to use after 10 minutes now from now for various engineering document and information follow up for downstream department, like that's what we are going from the design data, like what's his name, Faiz now is working in a project team. He will get a design data. We have this amount of gas, we need to make a gas plant, for example. We have this amount of oil, we need to make an oil plant. We're going to illustrate this one by one. This is the design data that's coming from the feed stage. We need to understand the process and instrumentation data sheet, piping and instrumentation diagram. We're going to make line list, which will be your first, schedule and line list would be your first assignment. Input for other process area, if we have the battery limit or package units. Package units, what's the meaning of package units? Any vendor who will supply a unit for yourself. Like what? Like what, Naja? Naja?
Like pumps, compressor.
Totally right. In our final project we are going to deliver at this course, we will have pump units and compressor units. We need to deliver them. I will teach you how to make contact with the vendors, how you generate these data sheets, how you acquire the vendor data, then you implement it or integrate it in your piping and instrumentation diagram to make the as built at the end of the project. Okay. Basis of design. Basis for preparations of mechanical design diagram is the basis of design. What is the basis of design? It is the first issuing document we are going to deliver, especially in the feed or in the detail stage. There. Then we have the process flow diagram, then we have the material balance, then we have the material selection report, then we have the material equipment data sheet, or equipment data sheet, sorry. This is the steps where our 5 days will be working. Today we will learn the basis of design and how it must be our pipe in the full project. Then we're going to make the process flow diagram. I will share one of them with you. Then we will open the hyses and make them a heat and material balance for the equipment. Then we will make the output from the hyses to the process data sheet and fill it to be sent for the vendors. Is there application code for the design? Yes, the most common is ASME, American Society of Mechanical Engineers. ABI Petroleum Institute is one of the most common for the depressurizing and make sure the mechanical integrity of the pressurized vessel. Then we have, if we are working in UK, for example, you will have the UK law for the regulations and the codes. Okay. Mechanical design diagrams. Data to be shown in the mechanical design diagram. At each individual piece of equipment, as well as the main piping, the following data must be shown. Like what? 1. Operating pressure, operating temperature, design pressure and design temperature, piping classes and specification break, piping plug valve, only if these valves can result to design condition, plug in, like we have plug valves at the outlet of the separator. We're going to speak about them. Check or non-return valve, temporary brake or material and surface brake. All these conditions we need to show on the P&ID and we need to show on the mechanical design diagrams. Temperature switches, also safety valves and rupture disc if there are any, elevation of the vessel and towers, air condition, air coolers, air cooled heat exchangers, atmospheric boiling point, will startup lights. Are we going to show the startup lines on the P&ID? Yes, because it is the key for your plant. Okay, why we are using mechanical diagrams? And this will be in the commissioning phase. Why? We have additional use for the mechanical design conditions, which will be in the commissioning. If we're going to steam out condition, we're going to prune with the steam, or drying condition, or vacuum condition, or regeneration condition, startup conditions, and short duration condition. All this can be extra additions for the mechanical design diagrams. Yes. Failures. Do we have failures? Yes, we have a lot of failures on the process design. We need the mechanical design diagram to identify failures for the determination of the mechanical design temperature and mechanical design pressure. Which failure we are suffering. This can be shown on the internal HAZOP we are doing inside our engineering firm, or can be done with the third party when you making or bringing a HAZOP Sherman like third party. Which failure we are trying to avoid? Power failure, cooling water failure, instrument air failure. Let's ask Naja. Naja, what happens if you have power failure in your plant?
So the process will get shut down, and there might be so there can be some issues with the pressure, temperature. For example, if cooling water pump is shut down immediately, then the temperature might increase. Reaction, it is difficult to control the reaction immediately.
What is the worst case happen?
Worst case, it can end up in a runaway reaction, a kind of explosion or
Fatality?
fatality. Yeah, right.
Yes. That we are trying to avoid by mechanical design diagrams. How many layers of protection we are going to install? Fayez, are you there?
Yes, please.
How many layer of protection we are going to install for a simple pump?
It depends on the consequence of the risk. I mean, if it is a fatality, the ultimate risk, for example, is a fatality, is different than if it is just lost time injury.
Let me say it in other words. It's the layer of protection which is coming with the pump or separator or even a reactor or reformer in a refinery should be different depending on how many fatalities we are going to catch. If we're going to kill one, then we have a low one layer. If we're going to kill two, we have two layers. Is that what you're saying?
Yes, I mean, it depends on the company policy. What are the risk level that the company will tolerate?
Yes, but
So when the company fatality, they will go to the highest, I mean, number of barriers.
let me say it in another word. What is the minimum for if you're going to design a pump? If Raja is going to design a tower and Naja is going to design a tank, how many layers of protection should they have at least to pass the HAZOP as a process safety review gate? One layer, two layers, three layers.
I think it will be also related to the consequence. For example, if it is a water tank, it's different than if it is a hydrocarbon tank.
Totally right. How many protection layers will you need for a water tank and how many for a hydrocarbon tank? Give me numbers. I want to feel it.
For example, just generally speaking, if it is a water tank, maybe 2 layer will be sufficient.
Okay. And hydrocarbon tank?
Again, it will be depending on the consequence. For example, of the overflow. But I would guess maybe three layer protection, at least 1 layer more than the water tank.
Okay.
It will depend on the consequence, the size of the tank, the overflow consequence, for example.
Perfect. Just to highlight something, there is API 14C, which representing the minimum design layer of protection for every single equipment we are known. So when you're challenging for the minimum of the layers, you simply refer to the API 14C. API 14C give you the minimum for the pump, minimum for the tank, whatever water or hydrocarbon, minimum for tower, minimum for high pressure, low pressure interface, which cause the fatality and the explosions. That is the most common failures you are searching for. There's a lot of partial failures like closed outlet on the vessel. We're going to use this in the depressurization. Then we have the loss of fans and mechanical failures and abnormal heat input. We are going to challenge all of this during our P&ID design. The most important part, we are going to identify today is to define the operating pressure and the maximum operating pressure. Operating pressure is the gauge pressure which exists inside the equipment and piping during the intended operation. How many gauge, how many bars, how many psi's you have from your fluid. Maximum operating pressure is the highest pressure which provide flexibility for the control of the intended operation. If the maximum operating pressure is not known, take 1.05 from the operating pressure. Do you know this word? You see this sentence? That's not right. Why? ASME P31, ASME 8, make a new, let me use my pen to draw something here. Why it's not drawing? I don't understand. Everyone can see this?
Yes.
Okay. At this point, this is the material. Ductility sheet. What is ductility sheet? Any material, if it is going heating, it will have a failure point. This is the failure point for the material, which is lose all its physical properties. The physical properties of like what, which we are interesting for the metal sheet of the separator of the tower is the hardness, how it's been solid and how it in this point the hardness fail dramatically. Here at this point is almost 3.5 times the design pressure. What's the meaning of the design pressure at this time? It is not the design pressure we are saying on our B&ID. Here what we are referring is the maximum allowable design pressure, which is equal to 3.5 our design pressure. I don't get it. Why you are saying a lot of things like this? Why we are saying this now? Because at this stage or this slide, we need to define the maximum operating pressure from the operating pressure. Let's assume that we have let's assume we have a Christmas tree which is producing gas with like 70 bar, and from this 70 bar we are going to have a separator from this, and from this separator we have another downstream equipment. The question is the design pressure for this separator if it is operating with 70 bar. Should it be here and here and here? Here will be the operating pressure. Here will be the design pressure we are writing. Here will be the hydro test pressure. The equipment should see on in the workshop. Here is the 70 bar we are speaking. At this point, this would be 70 bar multiplied by 1.3, which is the new limitation for the ASME. For the hydro test will be the 70 bar multiplied by 1.7 of the sheet of the design pressure of the operating pressure. Based on these numbers, this will be, can anyone calculate 70 by 1.3? This would be like 90 bar, the maximum design pressure we're going to write on the beyond ID, and this would be almost 120 bar for the hydro test. I think you didn't get it, right? Hello?
No, I think it's clear.
Anyone work for a new plant, or anyone who went to the workshop before, he understand that this what is coming from the process itself, from the basis of design we are going to see today, which is like is a gas coming from the Christmas tree. Then what is the limitation from the ASME code? And the hydro test pressure is the maximum pressure we can get before the material lose its hardness and its physical properties. That's why in a practical example, if we have a 70 bar fluids like gas fluid or oil fluid coming with a 70 bar, the design pressure of the equipment which holding this gas should be 90 bar. The hydro test for this equipment should be 120 bar. That what we are going to do, and that we are going to make especially for the line list, especially for the equipment list you are going to generate for the upcoming PFD. Mechanical design pressure. We have one upper, we have one lower. The upper is the pressure at the top of the equipment that is used to determine the minimum thickness of equipment elements under consideration of the upper mechanical design temperature. When we are going to define a design mechanical design pressure, we have to stick it with the temperature. Why? Because as per ASME division 8, the design pressure is fluctuating with the temperature. If we have a design temperature raising or operating temperature increase, that means the design pressure will reduce. That means T is always against with the pressure. As the temperature increase, as the design pressure of the equipment start to decrease. That's why when you define the design pressure of any equipment, you need also to define the design temperature for such the same equipment. The lower design mechanical design pressure is the subatmospheric pressure at the top of the equipment. Item subject to external pressure should be designed for full vacuum, except if we can prove them only partial vacuum can occur. Full vacuum equipment, we are always afraid from full vacuum when we have atmospheric tanks. That's always designed for a full vacuum. When we have a separator working under almost below 100 psi, we design it for a full vacuum also in case of depressurizing. Okay, shut-off pressure. Shut-off pressure is the maximum pressure of a centrifugal running pump or a compressor at zero flow. Okay, let's ask Naga. Naga,
Yes. Yeah.
do you have a compressor in your plant?
Yeah.
What is the operating pressure of the discharge for this compressor?
You can say 80 bar.
What?
80.
80. What is the shut-off pressure of your?
PSV 87.
If you're going to design a pressure safety valve for this compressor, you will design it for the which one? 87 or 80?
The maximum operating pressure is 80 and the PSV at 87. 87 is PSV.
Ah, I get it. This is the setting for the pressure safety valve, right?
Yes.
Okay. That give indication for us that the shut-off pressure for this compressor is less than the 87, can be 85. Why I said it is less than 87? Because if it is equal or higher, this pressure safety valve will suffer before the compressor shut off. We are going to link this deeply in the compressor design section. Okay, we have a shut-off pressure for centrifugal pumps and centrifugal compressor, which in coming, let me just remove this. What is this? This is the pressure and flow to be like this one. As the flow go to the zero, the pressure reach the maximum. Normally our operating condition will be here. Normally our shut-off pressure will be here. Most vendors or most manufacturer trying to keep this from 5 to 10% to make sure that not this compressor will not making a lot of working or electricity or consuming a lot of fuel. What we are trying to say here is that please, when you define your maximum or worst case scenario for the design pressure, consider the shut-off pressure, this point, and do not rely on the operating for the compressor or even the pump. Why we are using this, why we are afraid from this? Because sometimes when we have a centrifugal running pump, especially in LNG activity, most designer going for the operating and they totally ignore the shut-off valve. This lead a lot of, if you hear about the accident happened here in Egyptian LNG because of this shut-off pressure of the pump. The pressure increased dramatically in the pipeline, causing the pipeline to rupture. Okay, is it clear?
Excuse me, Mr. Said.
Yes.
So the shut-off pressures that without recycling the fluid inside the pump, so just close the discharge valve and that's it, and make the pump or compressor working at its highest pressure or performance. Is that the case?
Okay, it's a new voice for me.
Yeah, Mohammed, yeah.
Good morning, Mohammed.
Good morning, Mr. Said.
What I am trying to say is that when we have here any, let me make a new table which will be easier. Any pump have its own curve, right?
Yeah.
Okay. The curve was always coming from the pressure and the flow rate. The curve is coming like this shape. As long as the flow increase, the pressure increase, the pressure reduce also, right?
Yes.
The shutting pressure is the maximum pressure at almost zero flow.
Yes.
This is a phenomenon happen because the centrifugals or the impeller of the compressor or over the pump is reaching its maximum velocity because there is no fluid inside the housing of the compressor or even the pump, because the flow is almost zero, as you can see from here.
Yes.
So
Yes.
this means the impeller will reach its maximum velocity. Once it reaches maximum velocity, it reaches maximum pressure, which in this case is called the shutting pressure, which is we are afraid from this one, because if normally we have a pump and we have a pipeline, this pipeline is coming with a design pressure and this pump is coming with a design pressure. If this pipeline design is not higher than this line will have a rupture. You start to get it or
Yes.
no?
Yes, yeah.
That's why we always take care about this design pressure. The design pressure here is equal to 1.2 the shut-in pressure. That's why you can judge the pump if it is a high pressure or low pressure by the type of the housing, type of material of the housing. If it is making from a stainless steel, or if it is making from high milled steel, or if it is making from cast iron. There's a big difference between the design pressure of each pump, and based on the pump design pressure you are going to use the pipeline. Okay?
Yes.
Okay.
Another question, please, regarding the design pressure or temperature for any component. So during operation, reaching to the design pressure or temperature will lead to the equipment or component failure, or reaching to the highest pressure or temperature will just like make the failure. I mean, during operation will be okay to reach the design pressure for some reasons.
Do you attend this slide?
Yeah.
Okay. Here is the point of failure. When you reach 3.5. Normally, as a rule of thumb, when you're reaching 2 design pressure, 2 times the design pressure, your weakest point will start to leak, which will be the flanges.
Yeah.
But when you're reaching 3.5 time, the equipment will have a rupture.
Yes.
Okay. Why we are making the hydro test one time in the lifetime of the any equipment? 1.7 time. 1.7 the design pressure. Because the molecules of the steel sheet which manufactures the separator, the tower, whatever, is going to have internal forces equal 1.7 of the design pressure. These molecules will be stretched a lot. So we normally don't want this equipment to be stretched more. The 1.7, the equipment shouldn't see the hydrotest pressure any except one time on the manufacturing workshop. When it's coming to our plant, normally operation, maximum design pressure, and when we go to the 4-day, day number 4, we're going to speak about the pressure safety valve and the setting for the pressure safety valve in all the 27 cases. You will see the difference between the how we are, if we're making for this separator which is operating at 70 bar, and we have a design pressure for this separator like 90 bar, we are going to set our pressure safety valve for 1.1 the design pressure, or 1.2 in case of fire, which will be the maximum we can reach. This all come in a detail on the 4th day, don't worry. The most important part for me is that yes, you can go from operation perspective and from the design perspective, from mechanical perspective also. You can go from this 70 to 90 without any problem. Above 90 is the problem. The question is the age of the equipment make it difficult to reach the 90. Maybe yes, maybe no. Depend on what? Depend on the metal thickness. What does this mean? Normally, when we are going to design a separator like this one, and we have a metal thickness like 60 millimeter. Day one in operation, I can go from 70 to 90 because I know this 60 millimeter is still there. But you do normal corrosion rate. If there any upset condition like erosion, the 70 can be go to 50, and in this case you cannot reach the 90. So that's why you have to make sure that the initial thickness is there. If it is not there, you have to derate your equipment. Derate your equipment mean if this equipment nameplate coming with a 90 bar G design pressure, that was because of the 60 millimeter for the metal thickness. Now it is 50. It should be within 80 bar G, and the pressure safety valve setting should be calibrating based on this 80 bar G. Did you got it, Muhammad? Muhammad,
Yes, thank you very much. Much appreciated. Thank you.
this is called
And the,
risk-based inspection for your asset
Yes.
integrity department. They making like this.
yeah, and the thickness should be, for example, for vessels and any of the equipment, just like it will be the average thickness you will get for the whole.
The weakest point, Muhammad, not the averaged. The weakest point. If this separator have 1 point here and 1 point there, this is
Yeah.
88 and this is 70, we will show the rating to the weakest point.
Lowest, yeah, just to avoid the rupture. Yeah. Okay, thank you very much. Much appreciated.
You're welcome. Okay. Here we are. For non-liquid full systems, the design pressure shall be estimated in accordance with the following tables. These guidelines is coming from PB1, British Petroleum. How many participants we are? 1, 2, 3, 4. Okay. Before we finish, I will share with you. Let me see how many cameras we have. Specifications. Okay, we have BP, we have Shell, we have Total, we have ExxonMobil. Okay. Every one of you will be subjecting to make sure that we have the plant specification according to his client. Let me say it. Naga, your client will be Shell. Raja, your client will be BB. Faiz, if you want Aramco specs, I have it. Muhammad, who will be ExxonMobil. Okay, everyone?
Okay.
Why I'm saying this?
Okay.
Because every one of you, when he going to develop his own B&ID, he need to make sure that his client is satisfied. He need to make sure that his client is satisfied. Satisfied according to what? According to his specs. So, Naja, your client is PP, or Shell, sorry. In this case, let me write in front of each one. Naja will be Shell, Raja will be PP, Faiz. Are you satisfied with Aramco, Faiz?
That's okay.
Okay, and Muhammad will be ExxonMobil. No, you will take Total, Muhammad. Total is much harder than ExxonMobil. Every one of you are going to develop basis of design for the plant we are going to make, which will be a typical oil and gas plant, model compression. I will explain it specific. I will need the P&ID. I will share with all of you the PFD. From your side, I will be satisfied if you're drawing your P&ID in a Visio, Microsoft Visio, or even you draw it with a pencil on a white paper. I do not care. I am caring about how you are going to apply the philosophies of the basis of design you are going to explain. Okay?
Okay, Ustaz.
Let me complete this. Maximum working pressure. If we have less than 70 bar, you can use the maximum working pressure adding 1.7. Not, if you remember, we here multiply it by 1.1 and 1.2 and 1.3. All these companies different from each other. If you are going to work in a Wally Parson or Citran in the Middle East, you will have a different margins here. Different margins. 1.7 if you have 17 bar G to 40 bar G, you can add 10% margin. If you're going to work between 40 and 80, then you get the maximum operating pressure, and then you add up 4 bar G. This table is different from company to other. Different from company to other. That is depend on the company specs. You will be reading and telling me the difference. Okay, operating temperature, maximum operating temperature. What is the difference? What is the difference between operating temperature and maximum operating temperatures? The operating temperature, what we are going to see from the heating material pellets that we are going to generate today using Aspen Hisense. Maximum operating temperature is what we should get from the code to make sure that we are selecting the right material or right equipment thickness. The maximum operating temperature is the highest temperature which provide sufficient flexibility for the control of the intended operation. Why we are afraid from this? Why we are afraid from this maximum operating temperature? Because normally if you are using mild steel or carbon steel, the lowest temperature you can see is minus 29. Minus 29. Below minus 29 Celsius, the material will have some brittleness, and if you just hit it with any hammer, it will be like what's called like glass. So we have to make sure that this metal not go below the minus 29. This happened with me personally during the startup. I was in Emirates starting up a platform. It is a gas plant, gas well, and when the gas well we're going to start, I surprised that the subsea pipeline was carbon steel. The reservoir temperature. Let me draw it. It would be a nice demonstration of what we're saying. Okay. Here is a Christmas tree. Here is the production wing. And here is the subsea pipeline. This subsea pipeline is a carbon steel, which minus 29. And here was like 80 bar G. And here is the maximum pressure is almost 100 bar G. This happened with me when I was in Operation Naga. When I open this valve, this pipeline is free, only have 0.5 nitrogen pressure, 1.5 bar G nitrogen. I surprised that when we are opening this valve, start to fill this free pipeline or empty pipeline, due to the 80 bar to almost zero at the beginning, we was going like minus 35. See, minus 35. See, it was like a disaster for us. Why? Because the maximum allowable working temperature for this pipeline was minus 25, and now you're asking, is the process actually is reaching this going to minus 35? What we are going to do is we start to fill of the gas till it reach minus 20, then we stop, waiting till the pipeline gas warm up by the sea water. Then we start to add more gas again, waiting warm up by the sea water, add gas a little bit more till we pressurize all of this. Do you know, the plan operation for this was 2 hours. You know how much we take, Naja? 2 weeks. Because of a design mistake. Did everyone get my point?
Yes.
Yes, yeah.
That's why I start with the mechanical design diagrams, not the typical P&IDs. Typical P&IDs in most engineering firms are like a copy and paste, not a big issue. We will learn how to copy and paste today, don't worry. But the most important is the numbers in the P&ID. That's why we are learning the maximum and minimum working pressure and temperatures. Okay. Upper mechanical design temperature is the highest temperature at which equipment may be subjected to as a result of a failure. This is the most important part if you have a reactor, exothermic reaction in your plant, especially in refineries. If we're going to have a catalytic reactor, catalytic cracking reactor or reformer, this exothermic reaction and this reaction can continue forever, reaching temperature which is unlimited. What will be the maximum design temperature for this? Normally they have like 600 Celsius temperature. It can reach to 800 very easily. You have to consider the maximum, but in this case you say in few minutes that there's no maximum, it can't reach to the end. How are we going to change this or make this not happening? The normally is 600, the maximum we can reach it in 2 hours of operator ignorance is 800. So we are going to design for the 800 and make additional precautions like cooling the reaction by using the cooling water. This is one of the common mistaking in the design upper temperatures. You got me or not?
To be honest, not really.
That's what I love.
One question to make it more clear. Most of the company are using the credible scenario for the maximum temperature, for example, and maximum corresponding pressure, or they use the worst case in both in each parameter.
Which company you are speaking about? Operation company or?
Generally, the different companies, they are using to design equipment for credible scenario for the maximum pressure and corresponding temperature, or they are using the worst case in each to design an equipment.
Time. Here is the reformer. Here is the outlet of the reformer. Here is the outlet. And here is the jacket which we have the cooling water. Cooling water in, cooling water out. What I am trying to say is normally reforming reaction is coming to have like 600 C. It can reach 800 C. Also it can reach, if you are ignoring it, Muhammad, it can reach 1000 very easily.
Yes.
How can we design the metal for this reactor? If it is can reach 1000, if we are ignored the reaction for like 2 days, it can reach 2000 C very easily. Which point you're going to stop? 600, 800, 1000, 2000. This reach after 15 minutes, this reach after 1 day, this reach after 2 days. I want to listen to your thoughts, Muhammad. 600, 800, 1000, 2000. If you're going to design this reactor,
So what is the required temperature for the operation? Is 600?
yes, this is a normal one.
Yes. But this is the exothermic reaction or endothermic inside?
Exothermic.
So it can reach to 800 or more than this?
2000.
2000.
Look to the duration. 15
Yeah.
minutes here, 1 day here, 2 days here.
Yeah. Yeah, so 600. and it can reach to 800. Yeah, so using 600, maybe 800 or 1000 with the aid of the cooling tower, cooling water, sorry.
1,000 is after 1 day.
Yeah, so
Let me
so
make
we,
it, let me make it.
I think
Okay, tell me.
I mean, we just, I'm afraid of just like in case that there is no cooling water, so we need to avoid such a scenario because this will affect our process in here. So, so after 1 day, it's 800. To be honest, I'm not getting it, but I think 800 is okay. Should be fine.
When you're speaking, I listen to a word from you that you are afraid of. You don't have a cooling water, right?
Yeah.
You can't. You can't. And Raja, correct me if I'm wrong. You can assume two failures. You assume that the cooling water is failing, and the operator is not there. So this reaction will end forever, and even the cooling water is not there. Right, Muhammad?
Yeah, right.
Any engineering cannot protect you from two failures. There is no engineering can protect you from two failures. Even when going to hazard this at the end, we are always saying that please not to jeopardize two causes of failure. We're only tackling one. So
Yes.
normally here we are assuming that the operator will going to have a lunch for the first 15 minutes, and the reaction going the 800. Then we are designing for the 800. Then is that everything? No, we will add it safety instrumentation system. We're going to speak about this in detail on the first day and the fourth day. Safety instrumentation system is going to stop the reaction by cooling water. It will not waiting for the operator to start the cooling water effect. No, it will start the cooling water effect without the permission of the operator. That's why it's most important for us to know the cycle of any equipment. The cycle of any equipment. That's why you are going to learn how to make the heat and balance today. You got it, Muhammad?
Yes, thank you. So, what is the just like what you mentioned, the cycle of any equipment? Where can I find it from the mechanical data sheet, or there is just like a special, just like documents to can get such information?
Which information we are speaking? The 600, 800,
Uh,
1000?
So both the operating manual and the data sheet, so you can just like draw such cycle for each equipment that you just like draw here from 600, 800, 1000, something like this.
This is coming from the operation background.
Ah,
If you want to learn about it, you have to learn the technology itself.
yeah.
The technology itself for the reformer, for the catalytic cracking, for the separation, normal separator. We will learn how to design a normal separator in this course. A three-phase separator,
Inshallah.
inshallah.
Okay, inshallah. Inshallah. Thank you. Thank you very much.
Welcome. Okay. Here is the cases of to be considered: the operation failure, operator is not there. Lowest one day mean ambient temperature. The temperature is going below the design temperature. So the question is, when we are considering the mechanical design temperature as a lower, what we should consider? In Oman, what is the minimum ambient temperature, Naja?
Sorry, exactly, I don't have an idea about it.
You just give me the coldest day you have been in Oman. Tell me your coldest day.
Coldest day, it will be around, in my experience, it was around 11 degrees centigrade.
11 degrees centigrade. There is a lot of companies say that for the minimum you will take this 11 and you will add it extra 5 Celsius below. So if it is 11, we will go 11 minus 5. This will make our minimum design temperature will be minus 6. Minimum design temperature will be minus 6. This is one of the cases we can consider it. So the maximum design temperature and maximum design temperature for the high or for the low. The high, we can consider the maximum operating temperature we are reaching. Let me ask a question. In a normal three-phase separator, which is a static equipment, and there's no reaction to the physical disconnection between the fluids in each part, what is the maximum operating temperature will be your maximum ambient temperature. That's why in the basis of design, one of the most critical parts we are identified in the project specs. If you are going to make this project in Alaska in USA, or we're going to make it in like South Sudan or Congo, where the stream or the temperature minimum ambient temperature is 55. This is the cases we need to consider on the basis of design. Okay, we speak about this piping specs. Here is piping specs for ABB. If everyone download the link on the chat,
I'm accessing, Doctor, I'm accessing from my mobile. I'm finding difficulty to access the chat, but able to locate it.
just if you have, it is a Google Drive link. It is open for everyone. Just if you click it, you will see that I upload yesterday a full project we're going to deliver. This project, let me give a brief about this project, will be good before we start. Here is some of the process, our piping data sheets, piping classes and names. Here's some of the specs from ABB. Piping class stainless steel or even a carbon steel. A01B is carbon steel for ABB company. ABB company is using A01B for a carbon steel and using A22B for stainless steel. That is the specs of ABB company. Is it different from Total, PP? You should tell me. Okay. The centrifugal pumps, shut-off pressure of a centrifugal pump depend on the following: normal suction pressure, maximum suction pressure, pump different head, maximum pump different head, type of the driver, if it's a fixed or variable speed, and the capacity of the pump. maximum design pressure equal the B pressure normal section plus delta B, which maximum weight delivery pump can deliver, or the section and delta B normal. B normal section is a normal section, normal pressure in suction vessel and static head at normal liquid level. This would be very difficult in hydraulic, especially if you are going to do it with Excel sheet. B maximum section, set pressure of the pressure relief device of a suction vessel and static head at the maximum liquid level. This will come in more details when going to the hydraulic. The most important part at this time for me is that you understand that there is something called shutoff pressure. Shutoff pressure for any pump can be designed or can be calculated by, you have the normal section and you have the delta P maximum for the pump. This is the most important part for me at this point. Delta B maximum is the pump differential pressure at zero flow. At zero flow, based on the maximum liquid density. Okay. Reciprocating pumps. Is it different from centrifugal pumps? Yes. Can we have a shutoff pressure for this pump? Yes. Are we going to protect these pumps? Yes. There's a mechanical engineering say that you don't afraid from the mechanical pump, mechanical reciprocating pump. You just be afraid of the piping downstream this pump. Why? Because this pump is normally sending the pressure to the pipeline, normally squeezing the fluid inside its cylinders to pump the liquid to the pipeline. If the pipeline have a blockage, if the pipeline not flowing in well, if you close the valve in front of this pump will squeeze the liquid more to get rid of any obstacles in front of this pump, and that will make or you will end by the pipeline rupture. That's why we always have a pressure relief device installed on the discharge line of the reciprocating pumps. Naja, you have reciprocating pumps in your plant?
No, I am not in a process plant.
You have a centrifugal only?
I am not in a process plant.
You don't have pumps? Any
No.
pumps? Ah, okay.
No.
Mahmoud, you have pumps in your plant? Muhammad or Mahmoud? Mahmoud. Muhammad, sorry. Muhammad. Hello, Muhammad. Okay. Faiz.
Yes, we have. Especially the one that those chemical addition pumps.
Thank you.
Chemical.
These pumps always are coming with a pressure safety valve on the discharge to make sure that in case of the blockage of the pump, this pressure safety valve or relieving valve will take the liquids, which is oil, chemicals, whatever, to a safe location in the state of making damage to the pipeline. The maximum design pressure for the pipeline after the pump will be 1.25 of the maximum operating pressure of this pump. 1.25 of this pump. Okay, and here is the rotary pumps, which will be 1.1 if it is a fixed speed, and 1.25 is a maximum if it is a variable speed. For me, in a design, if I am making a design, I stick with the 1.25 to make sure that I am on the safe side. What is this? Last valve philosophy. What is the meaning of last valve philosophy? Why I am presenting this now? Because if here the pump is going to pump across this heat exchanger, second heat exchanger, then enter this vessel. If the control valve is the last valve between pump and vessel, then the minimum of the shell side of the heat exchanger can be determined as follows. Here is the flow going to the shell, and then entering to the vessel. If this control valve is the last valve between the pump and the vessel, if this valve is here, this means the shell of the heat exchanger should be designed to be equal or higher than the discharge pressure of the pump. But making this valve here, reducing the pressure of the pump and controlling the pressure of the pump, and assuring that it meets the shell design temperature, then the shell design pressure, to make sure that we are on the safe side, that shell side pressure must be higher than the vessel pressure and the static pressure, plus downstream piping and a heat exchanger. What is all of this? We want to make sure simply to not the design pressure of the shell here is higher than the discharge pressure here, higher than the vessel here. So when we have a fire case scenario, this will be the weakest point, and we are protected by this pressure safety valve. This is the philosophy of last valve philosophy. We are going to implement it during our design. Yes. Why? Because this is a kind of value engineering. Why? Because simply we can install a pressure safety valve here and another pressure safety valve here, and we will be safe. You know the cost of a 4-inch pressure safety valve? It's almost $10,000 US. That's why we are trying to protect all this by the last valve philosophy. I don't get your voice. Speak slowly. Tell me. Yes.
In this, there is no point to design for shut-off pressure because there is no valve downstream the heat exchanger.
Yes, this is a typical BFD, but in a normal BFD, in normal BFD, there will be category 2 valves for the heat exchanger for the maintenance purpose.
The question, doctor, here, why not to design for the shut-off pressure of the pump?
We are going to design for the shut-off pressure of the pump. Well, this one will be higher than the shut-off pressure of the pump, and this one will be the lowest one. The control valve here is going to reduce the pressure of the, let's say, be discharge, and it will be reduced by the effect of this control valve to be whatever for the vessel. When we are going to design the shell, we are going to design for this one, because if we design for this one, we will pay a lot of money, especially if you are an EPC contractor. That's one of the tricks for the EPC contractors. He designed for the vessel, he not designed for the shut of the pump by allocating this valve here. You got it, phase or not?
Yes, it's clear to me. So this also would be linked with the company policy. If they are not accepting this when it comes to as compared to the check pressure of the pump.
No, you
You're
face
not.
as an owner, you simply will ask for a valve here and another valve here for maintenance purpose if you want to clean this heat exchanger, right?
Correct. Yes.
And during the HAZOP you will simply say that one of your operator closes valve by mistake. That will lead to redesign all this according to the shutoff pressure of the pump. You got it?
Yes. Correct. Yes.
It is like a game by the end of the day. ABC contractor don't want to pay a lot of money for valves, and the owner want a lot of valves. Okay. Check valve for design condition prick. If we have a high pressure, low pressure interface, a vessel operating at a high pressure is going to give liquid to a low pressure vessel. We have to have a check valve in the interface. A check valve between the high pressure and the low pressure. This will be at your interest. For the temperature also, we need a check valve. Yes, this will help us during the drafting of the P&ID. This is the typical arrangement for heat exchanger. I'm not interested in now. I will show you a complete handbook for this typical arrangement, which will help you during your drafting. Centrifugal compressor, like centrifugal pumps, I will go for the 1.25 of the maximum operating pressure of the pumps, of the compressors. I will go for the 1.25 to make sure that I am on the safe side. There's a lot of specs. Some like Shell will go 1.15, BB will go 1.2, and ExxonMobil will go for the 1.25. The same here for the setting of the pressure safety valves in the downstream of the discharge centrifugal compressor. We're going to set it as the setting out pressure is equal to the pressure of the section multiplied by the vessel section, the volume of the section vessel, plus operating discharge multiplied by the volume of the discharge vessel over the total volume. Why we are making such hard equation? Because compressor normally come with two vessels, one for the section and one for the discharge. Each one of them have coming with a different pressure. Multiply this one by the vessel volume and multiply the pressure of the discharge by the discharge vessel volume and divided by the total vessel will give you the setting of the pressure safety valve. We will make it in detail when we are going to make the compressor day, don't worry. The most important part for me now is that you be familiar with the P&ID drafting, which we are going to tackle in a few minutes. This is the same table from another company, flow less than 17 will add 1.7, between 18 to 170 will go 10% margin, 170 24 8%, from 24 to 300 45, we are going to add 6%. This is especially for reciprocating compressor and turbines. The same pipe sizing, liquid flow. Okay, let me stop here. Let me open a new tab. Let me draw. What we are going to do. Let me stop sharing this. And open this. Can everyone see this now? Everyone seeing this PFD?
You can see a drawing, yeah?
Okay. Before we showing the drawing, I will start to say the intention of the project. Faiz, focus with me. Muhammad, Raja, Naga, please focus deeply on this. What we have a feed gas coming from one well. Everyone following me?
Yes.
Okay. This feed gas was normally coming before, in the beginning of its life, was coming with like 1000 psi. This was able to move along pipeline almost 100 kilometer to reach the plant. Central processing facility. Now, after 3 years of working, this 1000 psi reduced to become 400 psi. Everyone follow me?
Yes.
Thank you.
Yes, yes. We're following.
Now, this 400 psi is not able, from hydraulic perspective, to reach this CBF. We need to give a little push to this 400. How we can do this? By installing a typical gas oil separation plant. In other words, called nodal compression. How we going to use this? I will erase this 1 minute. Simply, we'll take from here and we will make a compressor and this compressor will go back to this pipeline. Simply where this 400 psi can go to the compressor, and the compressor can pressurize the gas to reach 1100 psi. Anyone have a problem? Okay, silence meaning good. Okay, we will agree on this. No?
The it is entering into the same pipeline. I think at same aged pipeline.
Yes, we'll make one isolation valve here to make sure that all the gas going to the CBF. This happened for all the gas wells, especially Saudi Arabia, for Aramco especially. The gas wells is pressure reduce, but still from the reservoir point of view there's still a lot of gas quantity still on the reserve. We need to extract it, but the pressure is not high enough to reach to the CBF. What we are going to do is
التشيك فالف اولا مش موجود.
باشا انا معايا مؤتمر بس
مؤتمر
خلص.
حضرتك؟ طيب
متقلقش،
طيب
انا
ماشي.
متابع معاك على الواتساب.
طيب ماشي.
ماشي. Sorry. Let's back to what we're saying. The gas quantity here is high. Normally we have 3 billion standard cubic feet, but the pressure here is not high to pump all the gas to the CPF. The little push we are going to use is utilizing this compressor to take the 400 psi to the compressor, and from the compressor it going back to the same network, going to the CPF, the Central Processing Facility. This is the main idea: taking the gas from a low pressure point, put the gas in a high pressure conditions. You got me or no?
Yes.
Is there anyone not understand what is the purpose of this project? Anyone want me to say it again? Any feedback? Hello?
It's understood.
Okay.
Yes, we can hear you, Doctor. Yes.
Okay, perfect. The feed gas here, which is coming, normally what we are receiving from a gas well is gas plus condensate plus water. The question is, can all these three enter to the compressor? No. This mean we need to install a separation unit here to separate gas from the condensate from the water, and the gas then will go to the compressor. And the gas will go to the compressor, what about the liquid? Liquid go to the flash drum, and from this flash drum we will have a pump, and this pump will also go to this pipeline. Oh, it's making different now. Let me share, because I'm a bad drawer, I know this. Let me share the PFD which I will go with to send it to you. Everyone can see it, so I can start explaining.
Yes.
Okay, what we have here is the feed. Let me, here is the feed coming this way. Then we have the first equipment we are going to see is the descender. The descender is a vertical vessel. The purpose of the descender is to remove any solid sands. Why we interesting, or we need to remove all of this? Because in the basis of design, as you will receive today, or if you download already the drive, you will see that the composition we are receiving from our reservoir engineering saying that we have a gas quantity, we have a water quantity, we have condensate quantity, then we have a lot of almost 20 kilogram of sand per day. Based on that, this 20 kilogram of sand per day, we need to remove it from the stream. Why? Because here is the compressor. If we initially take the feed from here, put it to the compressor instantaneously will be damaged. We need to make sure that only gas is entering to the compressor. How we make sure that there's only gas entering to the compressor? By making this separation. We need to separate sand, which is going to be here. We're going to separate sand. Then we're going to separate liquids, which is going to be in the separator, three-phase separator. We're going to separate the water and the condensate. Then we will take the gas to the compressor through this pipeline. After that, the compressor will pressurize the gas in this pipeline, going to the plant boundary limit here, joining back to the network again. But what about the liquid? Now I understand the way of the gas. The feed, gas, condensate, water, sand is coming at this point. Then entering the descender to remove the sand. Then the flow coming without sand. Still we have gas and liquids. Go to the three-phase separator to remove the liquids. Remove the water to evaporation pond, where water will be evaporated by the sun. Then we have the liquid condensate, which is very expensive. we're going to pump this liquid from this vessel to another vessel, which is V203, is the condensate surge drum, where all the liquid is pumping by a reciprocating pump to this pipeline, which meet the output of the gas pipeline. So liquid is coming, gas is coming, all mixed again, going to the CBF. Everyone following me or no?
Following.
Should I repeat it again? Anyone want me to say it again? Okay. We are going to design this plant. Typically, we will have a cold flaring system. Typically, we're going to have a fuel system. Typically, we will have a descender, a three-phase separator, compressor, another vessel, surge drum, and a pumps, reciprocating pumps. Today, we are going to draw all of this on Aspen HYSYS. Why? To get the heat and the material balance. Why? To make sure when I come here at this point, I know what is the mixture. When I come in here at this point, I know the mixture. At this point, I should know the mixture, and keep going all the process flow diagram. Then we will show you a typical arrangement for the compressor, for the three-phase separator, for the descender, for the pumps. Then I will let you with assignment to make sure that I want the P&ID for the descender, I want the P&ID for the separator, I want the P&ID for the compressor and the pump out. Okay?
Okay.
Thank you. You don't know how your voice when you're saying okay make me survive.
Don't worry, we are following. Even if we don't talk, we are following.
It's a problem that I don't see your faces, so I feel that I am speaking to myself.
Now, last year we get used to this online. It becomes our the way we do business. So
Okay,
we're now familiar with this approach discussion.
perfect for me. Let me share the basis of design. Okay. Here we are. This is the design. Here is the basis of design. The first document you need to issue for any plant you are doing. All the last 15 minutes I was trying to describe what we are going to do as owner company. As owner company. I have one of the wells reducing the flow pressure of the well. I need to increase the pressure of this well. Simply, I want to suck all the gas from this well and put it back to my network to make sure that all the hydrocarbons, if it is gas or liquid, will be back on my system. How I can do it? I tender it out as an owner company, saying I need to make a typical gas oil nodal compression where I need to separate gas, I need to separate condensate, I need to separate water. Gas will go to the compressor to increase its pressure. Condensate will go to the pumps to increase its pressure, and water will go to the evaporation pond where I will get rid of this water. That's what we are trying to do. That's what I am tendering out. Typically, if you're working or you're going to work in an engineering firm, when you receive this tender or ABC or whatever from the client, you will start to build your own PFD, asking how this objective, how this demand can be implemented on reality. What is the alternatives? Let me share this with you. Here we are. The conceptual process design. That's what you do, all of you I think. No one of here working in engineering firm, right? No one here working in engineering firm, right?
We work with from time to time as a client.
Sorry?
In my case, I am working with the engineering firm I am the client.
Yes, that's what I'm saying. That's your part here. As long as you are the client, you define the end requirement. Why you need this project. Define the starting condition. You give it to your engineering firm the boundary limit. Like what? Like saying to your engineering firm, I have a gas composition like C1 equal number, C2 equal another number, and keep on. And you define the objective of the project. Once you as a client you deliver this, we as an engineering firm, we start the conceptual design. We start to define the unit operation. Okay, to pump the gas I will need a compressor. To pump the liquid I will need an oil and pump. To make a separation I will need a three-phase separator. If we have a sand, I will need a desander to remove all the sand, and the filter if it is possible to make sure that there is no sand going to the compressor. That's what I will do if I work in an engineering firm or if I work as a process engineer in an owner company. Why? If I am process engineer in owner company, I need to make sure that I know the controlling philosophy of my company. If I am working in a SABIC, Aramco, ADNOC, Qatargas, even in Dalal and Oman, I know what is control philosophy I have in my similar plants. So I apply the same control philosophy. I need to make sure that what minimum unit operation I can achieve my objective, especially if I am working in the research and development process team. Why? To make sure that I am having the number of unit operation, I will need at least 15 equipment. I can, from the owner side, detect the budget for this. Why I need a budget for this? To save the money to make the project complete. So as a process engineer, I need to make sure that I have a lot of information about the equipment and the unit operation of each equipment, how much it will cost me based on the equipment I will draw, based on the process flow diagram I will develop, based on the objective of the project, based on the control philosophy which I will define. You got me?
Let's be clear, but could you tell me if it is technology, specific technology we could design from the licensor, flat licensing. If it is open arms licensing, we get it from the engineering.
Perfect. Based on all of this, we will provide input to the financial case. Visibility. Is it visible? Do we have money in our bank, or we need to make money to save money for 2 years to make this project happen? Based on that, we are tendering out. Once we are tendering out, you coming to the EPC contractors. Once the EPC contractor receive your tender box or tender mail, he will start for this minimum requirement. Define process definitions. Process stream properties. What is the gas composition you have? What is the pressure, temperature, quantity of gas we are speaking about? Any impurities in the gas? He will start to make his own required unit operation. Is it the same as you said, or we can use, instead of compressor we can use a turbine? Instead of the pump we can use another alternative, and he will start to make a lot of alternative for your site. Then he will start the process flow diagram, then energy balance, then a control philosophy, then cost benefit to timing to respect your schedule you want from us. Once we agree on this term, we're going to the detail. Let me say it from here. Okay. Phase. You're the one working the project, right?
Yes, currently I'm providing technical support to the project.
Perfect. Tell me the difference between the feed study and the detail.
From which perspective?
Eh? What you say?
From which perspective? The difference from which perspective?
The deliverables.
The deliverable of detail engineering will be more simply will be more detailed. For example, the BIND we develop the BIND on the feed stage, but we don't get into the detail of the package unit. We leave it for the detail engineering contractor.
Good. What else?
For example, SIS, it will not be very detailed design for the SIS, for the safety instrumented function. However, we will identify our requirement, whether it is L1 or L2 or L3. But the details will be worked out by the detail engineering contractor.
Good. Very good.
For example, to piping, typically we don't produce the detail isometric. The
Good.
isometric will be done during the detail engineering.
Very good. In a feed, if we're going to have a feed, make sure that all of the philosophy are presenting on the feed. Flaring philosophy, isolation philosophy, drain philosophy, operation philosophy, commissioning philosophy, construction philosophy. All the philosophies are going to be presented on the feed. For example, if Naja, as an operation engineer, he want to enter a tank for internal cleaning, which kind of isolation he will need before entering this tank? Should I consider human entering a vessel or a tank is visible for me or no? Naja, did you clean a tank before?
Excuse me?
No.
Do you?
No.
Did you clean a tank before?
Yeah, of course. We have cleaned, yes.
Okay, Raja, as a safety engineer, for a confined space entry, you need a double plug and bleed, right? As a minimum.
Yes, right.
From design perspective, we need to consider this as a design philosophy, as an isolation philosophy. We have to agree which philosophy we are going to implement. Based on what? Based on the equipment you want us to isolate. So, as Faiz said from the beginning, the criticality of the equipment, the functionality of the equipment. For example, towers. People can enter a tower? Yes, they can enter a tower. For internal inspection? Yes. So it is a confined space? Yes. So double plug and bleed and ventilation is requirement? Yes. This should be in the isolation philosophy. For example, let's say a tank, as we said with Naja, going for internal cleaning? Yes. Double plug and bleed? Yes. Pound limit for the equipment for the plant should have a double plug and bleed? Yes. Check valve to be installed when? For the high pressure, low pressure interface, as we said from the presentation? Yes. All of this have to be written and agreed on the feed stage. Why? When we are writing this as a philosophy, when we go into the P&ID, we are going to implement this philosophy on reality, on the equipment list we are going to produce. You got me?
Yes, it is clear. Typically, this is main deliverable of the philosophy mentioned, whether it is isolation or control or environmental design basis philosophies. We ensure that they are developed as a deliverable.
Totally right. The most important for me, that if you are going to process engineer, for as me and myself, I print this paper in A0 scale, and it is on the back wall of my office. It is coming from KBR, by the way. In the detail engineering, before we go to the tail, I will go to the basis of design, which is coming from which is coming from
Basis of design usually you finalize during the field stage.
صوتك مش واضح. Your voice is not clear.
It comes from even before the feed stage, and the client is developing this document typically. The owner, I mean.
Basis of design?
Yeah, we put a preliminary basis of design, what we need exactly.
Yes.
And then we develop it further with the feed contractor to make it more mature, and then we hand it over to the detail engineering contractor.
But take care, because a preliminary basis of design is a kind of how to presenting the scope of work. But actually, if you work in Wally Parson, if you work in Xtran, if you work in Technip, what we got from the client is a scope of work, whatever the names the client name it. Basis of design is what we are as engineering firm develop to make sure that we and the client I agree on the conditions, on the standards we are applying. What I opening now is the table of contents for the basis of this design. Have a look here. The project scope, definitions, appreciations, abbreviations, unit of measures. If your client love to see power gauge or kilogram per meter cube, apply code and standard, which will be different from company to company. Why you are saying this? Because shell specs, shell dip is different from ExxonMobil, especially in the pressurizing and depressurizing. Then rephrase your state of work phase. What we are getting from the client, we simply copy and paste here, saying what he want in another way. Then we have the process description. Then we have the system specification. Then we are referring to the codes we are going to use in the relief system, firefighting system, fireproofing system, fire and gas detection system, control system, we are going to say shutdown system, even the utility instrument, electrical and emergency generator, tightening and earthing, electrical cable, voltage levels, what all of this. And then the design cases and design criteria. Basis of design is a common document between, as you can see, all the disciplines. All the disciplines. What we are doing as a process engineer is these parts: the introduction, the scope. OTIC or on spec scope of work is to perform. This is our task, by the way. is to perform a complete detailed engineering package for Frascor Phase 2 gas compression station, comprising of 20 million standard cubic feet gas and associated with also all accessories and utilities. Whether the either Frascor Phase 1 free area would be utilized for the Frascor 2 layout. There was before another compressor called Frascor 1. We will make the second nodal compressor, which is Frascor 2. Okay, here is the objective, what we received from the client. Some definitions, some APIs, some abbreviations I'm going to use, unit of measures. This document is on your Google Drive. Applied code and standard, different from company to company, area to area. If you're working in Europe, it will be different from if you're working in the Middle East. If you're working in America, it depends. ASME, process piping, is equal to PIP, process piping in UK. ASME is the American Society of Mechanical Engineering. Here is a lot of ASME, a lot of APIs for the valve, for the process measurement instrumentation, transmission electrical control valve, and the pressure safety valve 527 and 521, recommended practice for pressure relieving and pressurizing system 520, 5201. All environmental testing, IEC, electrical, and all of this. Then here is the process description. A raw gas feed from the well to be received at the existing Frascor Phase 2 inlet manifold via existing flow line from the well. We have single flow line coming from the well. It will be connecting our boundary limit at the plant. The gases then shall be directed to a new online sand removal unit. We will have a sand removal unit to remove the sand from the process fluid. The sand-free process fluid shall then separate it into gas, condensate, water in a new three-phase separator, such that gases are compressed to and direct towards existing 12-inch 20 kilometer pipeline. Gases which is separated, we will pressurize it by the compressor, then pump it back to the network, the pipeline network, which is 20 kilometer pipeline. This is the gas way. What about the condensate or the liquid way? The condensate is directed to a new condensate surge drum. We will make a surge drum, which is typically a two-phase separator. A two-phase separator, then pump it also towards the existing 12-inch. It will also, the liquid will go mix again with the gas at the boundary limit, at the outlet boundary limit of this plant. This means the plant entering is gas, condensate, sand, and water. The plant outlet is gas and condensate. Then we have the water is directed to the produced water evaporation pond. Both gas and condensate, here we are, shall be commingled in one flow line and dispatch it to the Wastani plant through an existing 12-inch 20-kilometer pipeline from Shahbaz manifold to the EWCBF Wastani CBF Center Processing Facility. Okay, this is the process description we are trying to do. This is the process description for the process facility. Raja,
Yes, please.
here is the fire protection system we're going to apply. Relief system, it will be a cold stack, a cold vent. It will have 20 million standard cubic feet of gas to be dispersed in the worst case scenario. We will make a dispersion calculation for it according to API 521. But the most interesting part for you, I think, will be the fire protection system. We will have a firefighting tank with minimum capacity of 400 meter cube. Foam trailers, portable pumps, foam tank, monitor, hose reel, dry chemical powder, trailers, carbon dioxide, automatic floating existing system, clean agent, automatic extinguisher system for switch gear and control shelters, portable and wheel dry chemical, all required piping tie-in isolation valves, and complete firefighting system for frost core 1 and 2. Okay, a control system. All this will have its own DCC, DCS, and the software we're going to use are Rockwell Logistic 5000 BLS program, PLC program software. This is not interesting for me. This is the process part. And page 20, you will see the design basis. As you can see from this part, this is the technical data we are going to use as an input to our process simulation. What we have a design inlet raw gas flow rate 20 million scuff feet. Everyone, if you have a white paper and pencil, start write this condition. Are you following? Hello? Are you following?
Yes. Yeah.
Okay, start to write this, please. We have a 20 million standard cubic feet of gas. We have a condensate rate fluctuating from 240 to 1000 barrels per day. We have a water rate from 2000 barrels per day. We have a sand rate which is 20 kilograms per day. We have a design pressure from 250 to 900 psi. We over design factor, which we are agreed with the owner to be 10%. This is our design conditions. This is the battery limit conditions. What does this mean? This means that We have a section pressure from the well 250. We have a discharge pressure 110. We have a section pressure 50 Celsius. We have a discharge temperature 45. 50 is what is coming from the well. 45 is the ambient temperature. Here is the gas composition what we received from the client. Hydrogen is 0%. Hydrogen sulfide is 0%. Carbon dioxide is 0.3. Nitrogen is 0.04. Methane 87.6. Ethane is 4.47. Propane 2.6. And isobutane, normal butane till the 100%. Okay. What is this? Phase. You generate to your ABC contractor design cases.
Yes, we do, yes.
Sim-
But it depends on the business case, what we want at the beginning. And we agree on the business case with the steering committee of the project.
Perfect.
But that's typical. We ask the contractor to generate design cases, and most of our work actually with the licensor. So we try to agree with the design cases with the licensor before we go to the contractor.
Ah, good for you. Normally we have design cases. If you can see, we have the same 20 million standard cubic feet here. But the water is almost fixed. The only flow or only fluctuating is the condensate flow rate, which is coming from the reservoir team, saying that there's one case it will be the liquid 240 minimum and the maximum 1000. Also take care that the pressure will start from 900 at the top, then will go down till it reach 250 as a minimum. What is the difference? What will impact us? Naja, from operation point of view. Naja,
Yes, please. Yes.
from operation point of view, if you have a compressor can work from 250 till 900 psi as a suction pressure, the answer is no. Why? Any unit, any rotating equipment will have something called turn down ratio, which is the minimum quantity, minimum pressure, minimum quantity, minimum level, minimum temperature it can operate on. As long as this minimum is going low, this unit will not be able to work efficiently. This unit will not be able to work efficiently. What we should do during the cases, we have 3 cases, we should consider the minimum and the maximum. We want the same For example, pump here, we are going to pump condensate. We have 240. The pump should operate from the minimum 240 till it reach 1000. So we have to be selective to a pump which have a minimum operating flow 240 and the maximum 1000, and take in consideration the 10% margin or design margin, we agree on it. The same for the compressor here. For the suction pressure, we need to make sure that we have a compressor. It will take the suction pressure 250 till it reach 900, or simply the compressor can convert it from one stage to two stage. We speak about this in detail. Okay. Okay, Naja.
Okay. Okay.
Design pressure, design temperature. He, as a client or as an ABC contractor, he considers the 1.1 and 1.25 for the pumps, 1.1 for the static equipment, 1.25 for the rotating equipment. The design temperature, he considers the skin temperature to 85, and the minimum design temperature shall be 5 Celsius lower than the minimum operating temperature obtained during normal operation, startup, shutdown, or process upset, or 5 lower than the temperature occurring during cool down, including cool down when depressurizing is delayed, whatever is the lowest. I don't get it. You get it, Raja? I don't get it. What he is trying to say that I would consider minimum design temperature to be 5 degrees lower than the minimum operating temperature obtained during normal operation. If your separator is working at 50 Celsius, 50 Celsius, I would consider the minimum ambient temperature. Minimum ambient temperature in this area will be 10 Celsius. I will take 5 degrees lower than the minimum ambient temperature. Okay, if the minimum ambient temperature is 10 minus 5, okay, your design minimum temperature will be 5C. I can understand this. Or 5C lower than the minimum temperature occurring during cool down. Why he considers a cool down? Why he considers the cool down when the pressurization is delayed, whatever is the lowest? Because normally, as the example I give it about the platform, during the cool down, during the startup, during the commission, you can reach to a temperature which is very far from your minimum design temperature. So he will make a calculation. He saying in the base of design, I will make a calculation for the depressurization. I will relieve all the gas inventory inside the vessel to the atmosphere, and I make this calculation to make sure that to see the lowest temperature it will reach according to this pressure, 1000 psi pressure. And based on that temperature, I will design my metal or my piping system or my equipment to be 5 degrees less than this temperature. If this temperature, for example, was like 0, my design temperature for the metal will be minus 5 Celsius. And keep going. Okay. Here Turn down. Turn down. It was agreed with the client that the facility shall be designed to a turn down ratio of 30% rated flow rate. This means if we have 20 million standard cubic feet, this plant would be able to run if it is 7 million standard cubic feet. Okay. Design life. What is the design life? Lifetime of this facility was agreed to be 15 years. What is the difference if I said 15 years and you, Raja, say it is 30 years? You, Naja, say it is 25 years. And Muhammad, I miss your voice, you say it is 25 years. Anyone say to me what's the difference? Hello?
The difference.
Hello.
Yes, the difference you will invest more because you need to ensure the equipment will be surviving, for example, 20 years.
Okay.
So, for example, if it is a vessel, the corrosion allowance will be more.
Perfect. What else? Muhammad. Muhammad. Okay.
Yes, Mr. Said, yes.
What's the difference?
Yes.
What's the difference between
Between what and
lifetime, if it is 15 years,
yes,
and if it is
yes.
25 years? Okay, take your time to think. Raja. Raja.
But this, if the years are increasing, then the the strength, the integrity should be high. To the lifespan of the equipment should be high so that it can last for 25 years.
Okay. Normally, we design the plants for 25 years. BP didn't accept any plant design less than 25 years. Shell didn't accept any plant design less than 30 years, 30. ADNOC didn't accept unless 25. Qatargas 25, Aramco, all the plants was 30, now it is 25. The question is, why it is here 15 in this project? Why it is 15? The answer is because
Using
yes, tell me.
no, sorry, I just got it wrong.
Okay. The answer is that because the objective of the project, we are going to suck the gas from the well. Eventually, if we're taking 20 million standard cubic feet per day from this well, by the end of 15 years, this well will no longer have any gas. That's why we are making the project for 15 years as per the client request. But normally any design firm will go to 20 years unless the client go higher. 20 years, as Faiz said, it will save the cost, because 25 will require a lot of thickness. Make it mute Naga, please. Thank you. It will require more thickness for the equipment, and it will cost you a lot of money to fabricate such equipment. Okay, the design rates was 110, and the hydraulic calculation, we are going to make a lot of hydraulic next time. Utility, okay, mutability, I haven't any problem. Sparing philosophy. Sparing philosophy. Sparing philosophy. The question for everyone: what is the availability of your plant? Let's start with Faiz. Faiz, what is the availability of your plant?
It will depend from technology to technology. Is it by batch operation, the new ones?
Give me number
So,
for any one of this.
for example, continuous operation like Olefin, we expect it even to be maybe more than 95 here.
Good. How does this impact your design?
One aspect is the sparing philosophy.
Thank you. What this mean, Raja? This mean if we're going to construct a plant having one pump, if this pump fail, the plant will shut down. Based on the availability of the plant signed on the contract, and based on this, we added a standby pump to make sure that the failure rate of the pump will not be counted to the plant, will not be affecting the plant performance. If one pump fail, we have the other one standby to kick in. That's why we are speaking about the availability. Plant availability 95% mean that 95 multiplied by the year's day 365 will give you almost 18 day to shut down your plant, to make all the necessary turnovers, turnarounds, and maintenance you need to do. The minimum for accepting any plant is next is 95. Okay, that is for the sparing philosophy. Anything affects that plant availability will have a spare. Layout for this plant will be depend on the FERA study. Anyone know what's the meaning of FERA? Fire Explosion Risk Assessment Study. This will be done by FAST software to say if this separator, for example, have a pinhole and we got a jet fire, the impact of this jet fire on the nearby equipment. For example, if the flame length of this jet fire reach 12 meter, We should install the equipment beside the separator by a distance of 13 meter, 1 meter above the flame length. This is output from the FERA study. This output should be developed by the process safety, transferred to the piping people to make sure that the separator, for example, will be far from any other equipment by more than the 12 meter distance. That's why he say safety philosophy for the layout will depend on the FERA study. Okay, Raja,
Okay.
I will share with you my last FERA study for this project. It will be good
Okay.
for all of you, don't worry. Hazard area classification used for this plant will be according to IP15. It will be like, or our API 505, which is both. Zone 0, ignitable concentration of flammable gas. Zone 1, Zone 0 is the continuously persisting, the main process area. Zone 1, the vapors are likely to occur under normal operating condition like tanks. And Zone 2 for the utilities like the instrumentation, air, power generation, and all of this. We didn't have there any flammable gases. Okay. Metallurgical data, which is most important for us as a process engineer. Maximum ambient temperature, as we said, minimum ambient temperature, solar radiation temperature, 1 kilowatt per meter square. It will be very helpful during the flare dispersion calculation. Ground temperature will be excuse me, will be 40, between 17 to 40 Celsius. Wind speed for the civil people, nothing else for the basis of the design. Let's close it. Let's jump to the do you prefer to have a break for 15 minutes? Hello?
Yes. Yes. Yes, please.
Yes for break, or yes you answer?
For a break. For a break.
Okay. It is now like 12. We will take 15 minutes. Please, let's be American in time. 15 minutes means 15 minutes. When I come back, I will start with simulation to generate the heat and air balance for the Aspen HYSYS, for the feed we have on the basis of design. Then we'll end it up by Aspen HYSYS typical P&ID drawings to make sure that you are going to draw this for the next time. Okay? You start your break now.
Yeah, we can break. What? There will be lunchtime, or this is the lunchtime?
I don't know. It is my tea time now. Not lunch.
So what is the next? Will be straight to 3 o'clock. Means another 3 hours after this.
No, we will take 15 minutes, 15 minutes.
It is lunchtime for us.
What's lunchtime? How much time you want?
I don't know. Other people,
How much time you need to eat?
half an hour.
Time for prayer and lunch. So maybe 45 minutes should be fine.
45 minutes?
Yes, usually that's the case usually. It's up to you and to the team.
Let's stick with 30 minutes. Okay, 30 minutes for more than enough.
Okay.
We have we still have a lot of things to do. Simulation and typical arrangement. It will take a lot of time.
No problem. So it will be 30 minutes for prayer and lunch.
Yes, from now.
From now,
Okay.
no, prayer time not yet come.
Okay. What's the time now in Saudi Arabia?
It is 11:08 now. So usually prayer after 12.
Okay, you need us to continue 1 hour extra or what?
So 1 hour it will be UAE time. Our time it will be 12. The prayer time will start.
What's time now in Oman, Naja?
It is 12 now. 12.
It is 12 and Faiz it's 11. Muhammad.
Yes, yes, Mr. Said.
You are in which country?
Yeah, yeah, from Iraq.
Iraq. What's time now in Iraq?
Sorry,
What's time now in Iraq?
time is 11:04.
11, like Saudi. Okay.
Okay, then we break for a short this one and taken out 1 hour. We'll have lunchtime.
Okay. We will take 15 minutes now for drinking tea, coffee. Then we will come back. Then we will continue to the prayer time. Okay?
Okay.
We will consider this next time. Don't worry. Okay. 15 minutes break. Then we will come back. السلام حكايته عسل اتفضل على النور الأوضة في حاجة ولا ايه؟ أنا نازل النهاردة بعد الساعة 6. معرفش انتوا مش بتحسبوا النهاردة يوم شغل؟ لا أنا هعمل مبيت النهاردة. ايه؟ يعني ايه؟ ما انت كل الناس بتعمل كده، هي جت على هنا يا شيخ، ده على يدي. ما تصلي ماشي؟ لا يا بيه ما جاش والله ما عماد. ها؟
اما تخلص ها.
انا هنزل بكره ان شاء الله. ان شاء الله. بعد اسبوع. تسلم يا شيخ. اللي عامل اختاري على بكره ان شاء الله. ماشي. اتفضل. الشيء جاي؟ نقول خلاص الرئيس جاي، رد جاي غدا ان شاء الله. الرئيس رد جاي غدا ان شاء الله.
غدا
لا استنى دي بتاعت القديم.
ولا جاب لنا سير.
صح؟
ولع ولع الشيشه بتاعتك خبيها هو السير عم. ايوه انت مش هتولع.
مين حل لك الحالة الوحشة دي؟
امم
مين حل لك الحالة الوحشة دي؟
لا اي حاجه
ليه كده؟
ماليش ضامن نفسي.
ضامن نفسك ازاي؟ ايه الكلام ده؟ مش ضامن نفسك. انت جبت القهوة دي من مين؟
بتاعتك
ايه؟
بتاعتك.
دي بتاعتي؟ لا يمكن. لا يمكن. لا والله.
لا وحش يعني؟ انا ايه اللي حسيت خدت
Everyone in his mobile, if you open the first document, page 21, you will find the gas composition. Can you open it, please? Faiz, you and Muhammad open the page of design 21. Naga and Raja, please open the PFD. Hello.
Yes, I already opened the composition, page 21,
Okay,
composition table.
perfect. Muhammad.
Yes, I already see it.
Okay, page 21.
You mean OSP? Yeah, OSP 086, right?
Yes, page 21. Naja, did you open the PFD? PFD. Raja, the same PFD, please. Raja.
I'm getting it.
Okay, perfect. Let's start. Okay, please all mute. Muhammad, please mute your phone.
Yes, okay. I just want, because you already said that it is the page 21, yes. So I got this compression station. So this is for me that you are mentioned,
Sorry,
because I can't find any page in here.
I don't get it. What you get?
I in the WhatsApp group, okay, I got 2 files, which is one, the basis of design.
Yes, page 21.
So you mean page 21? Ah, okay. Okay, thank you.
Okay. As you see, the first and the most important part for your role as a process engineer is your understanding of HYSYS and how it's work. Why? The first thing, when you receive a tender from you as a client, we start to make the process flow diagram. As you see, as I said it to you on the website. Process flow diagram, here is the typical unit arrangement that we can arrange to reach the objective of your project. Is that all? No. There's a lot of process inputs, a lot of process outputs I need. Inputs is coming from the basis of design and the boundary limit and the ambient conditions, as we will see. Outputs will be to the other disciplines for piping, for the rotating engineers, even for the safety engineer for doing the fair studies when they ask for the inventories and all of this. The first step in every project is the simulation. The first step in any project is the simulation. Which simulation? Simulation, the PFD, the process flow diagram we are already drafted. To do what? To make sure that this PFD is achievable on HYSYS. If it is achievable on simulation software like HYSYS, it will be achievable on the reality. First, what I'm going to do, I share already a lot of materials for HYSYS. Please, and I will share the link for downloading the HYSYS for free, and I will share the steps I make it here. What will be requirement from your side to install HYSYS on your laptop. Please don't participate in mobile. It is not a theoretical course. Will be practical, very practical, and sometimes you will need a calculator. So make sure that your mobile or a real calculator on your side. The first thing in making HYSYS, when you open this one, make a new one. It is a very heavy software. Please try to install it on a very high performance laptop. New. When it's open a new scanning component list, fluid packages. This is the most two critical points we are going to discover today. The first part is going to add what? A component list. When we add a component list, here is a list for all the components in the worldwide. Even petrochemicals, whatever component you love to see, you can find it here. All the components you want to see. giving all composition. You can use normal components, pure components, or you can use hypothetical components. What we are trying to get is phase. As you the only one have a mobile, please open page 21 and start to tell me the components on the left.
Sure.
Hydrogen,
Hydrogen
hydrogen,
and hydrogen sulfide.
hydrogen. Here we are. I search it by the name, then I will click add first component on my left, then hydrogen sulfide. I can write it like this, or even I can write H2S. Both can be done. Then add. Then we have carbon dioxide, right?
Yeah, right.
Here we add another pure component. Then we have a nitrogen. Then we have methane, ethane, propan, isobutane, normal butane, isobentane, normal bentane. When I remove the first chemical come to us, our first component come to us is the methane, which is the C1, C2, C3, C4, C4, isonormal, C5, isonormal, C6. I will add it all till C6. Methane, here we are, ethane, propan, isobutane, normal butane, isobentane, normal bentane, and C6. If you open page 21, you will see that it have normal heptane and hexane and cyclobenzene and all of other chemicals, right?
Yes, correct.
For me now, for simplicity, I will just make this 6 component only. For a real life simulation, you have to insert all these components. Once I added all components, I will go for the fluid package. Fluid package is simply, do you remember from high school when we take the law which calling ideal gas law, PV equal nRT? Do you remember this law? Yes. This law has been modified many times to predict the behavior of the gas, to predict the behavior of the gases. Based on that, this one has been developed. I just first added, then the most worldwide common for gas without H2S is being propensol. For the LNGs, we go in RTL. The glycol dehydration, LKP. Based on what? Based on the constants which has been added to this equation, BV equal nRT, to predict the behavior of the gas. All of these are equation of states. All of them are used to predict the behavior of the gas. The most common is the Pinker principle. 99% of the process engineers work on fingerprints, except who working with LNG, they are working with NRTL. Okay? Anyone say okay?
Okay, mister.
In the component list here, I forget to add water. H2O, which is the water, right? What is coming from the well is gases, condensate, and water. We know the component list is okay. The basis is okay. We will go to the simulation environment. Simulation environment. When we're pressing the simulation environment, we are switching to simulate our plant. The people who have the PFD, Saja and Raja, right? Raja and Naja, sorry. Raja and Naja. Here is the equipment which we can draw. First thing, we'll define the material stream. The material stream, if it is shadow blue like this, or it is not dark blue, this means this is not defined stream. This is the boundary limit we are entering to our new plant. This is the boundary limit we are entering to our new plant. This is the gas coming to our plant. This is the feed from the well. We need to define it. Double click on it, then we will have this page. Typically, he will ask you for a lot of questions. The first one is unknown composition. So we'll go to the composition tab and start to insert the numbers we have. Faiz, can you tell me the number for the hydrogen? How much mole fraction we have of hydrogen?
Zero hydrogen, 0.1%.
Hydrogen
Zero?
is zero, yeah.
Good. H2S, how much?
Zero.
Good.
Zero.
CO2?
0.3332.
Nitrogen?
0.0478.
كويس. ميثان؟
87.6012.
إيثان؟
Ethan, 4.478, 58, sorry. Seven, 5, 8, yes.
Propan?
Propan, 2.6618.
Isobutane?
0.7506.
Isobutane?
0.6086.
Isobentane?
0.3738.
Normal pentane?
0.2026. 26, yeah.
Hexane?
Hexane 0.57. 66.
After hexane we have a lot of components, right?
Yes, yeah.
For simplicity, I can added all of these components in the hexane mole fraction, which means that I will add it from the bottom 0.001 plus 0.805 plus 0.153 plus 0.168 till I reach to the hexane. You got it, me?
Yes, yes.
طيب. Which by the end of the day will be like my 5.3, and the water
3.5. 3.5 or 5.3?
3.5, sorry, and the water will be like 0 now. We will come to say how much water we have. Okay, after all of this we say normalize, because the total of the load. Muhammad, can you make a mute?
Sorry. But just the hexane 3. Yeah, okay.
Tell me, don't take your time in asking. Don't worry.
So it just the network, is slow. So yeah, because it's still 5.3 on my screen. So now it's 3.5. No problem. Yeah, thank you.
Okay. For the water, I press 0 or put 0 now. As you can see, the total here is 10055 to the power of 2, because we have 8.7 here. Normally the mole fraction summation should be 1, only 1, but what I entered here is the mole fraction according to 100%. The Aspen Heises understand that this 100% is equal to 10055 multiplied by 10 to the power of 2. When we say normalize, sorry, as you can see, the total will be 1, and the 78%, 100% was now becoming 0.8712. The same shares are here for everything we entered, but relative to the total of 1. Okay. This is the composition. We got it from the reservoir engineer. That is the basis for our calculation. This is the feed N. Your voice is not clear.
It is very good quality natural gas. Nitrogen is very low.
Wallahi, I don't hear you. Your voice is not. If anyone hear him good, tell me what he's saying.
No, it's not clear. Yeah.
Doctor, on this side comment, the natural gas quality in this case very good, because nitrogen is very low concentration.
Which is good or bad?
Very good. In our real scenario, we are having much higher than this.
How much?
I think this is
how much higher?
Can go up to 10%.
Which is bad.
Very bad. Yeah.
Let's move from. I will make something for you. We will replace the CO2 concentration with the nitrogen concentration. Do you have any mind? Do you mind? Hello? love to play. Let's make it this 0.005 and make this 0.0033. Now it is almost like 5% from the 3%. Let's make it 1.5. Now it is clear 5%. Okay, 5% of our feed is nitrogen, which is more than enough. The other unknown for the HYSYS to understand what we need is the temperature. Then we come back to the conditions, go to the temperature icon. The ambient temperature from the basis of design was, anyone can answer me? Hello? Hello? Ambient temperature, maximum ambient temperature we are considering in page 26. In page 26 is 24 Celsius. This is the maximum ambient temperature. And if we go back in page 22, we'll have the design cases, which is temperature there is 50, which is coming from the well. So we will take the worst case, which will be 50 as operating temperature. Back this mentioned in page 22. Back to simulation and make it 50 Celsius. From page 22 on the basis of design, we have a pressure of 250, 500 and 900. This means we will make 3 simulation cases. For myself, I will make the 250. For you as assignment, Naga and Raja, please write. You will making the 500. Faiz and Muhammad, you will make for the 900. Okay?
Okay.
For me, I will write 250. BSIG. I'm searching for BSI here. BSIH. Did you see what happened? He started to make a vapor phase. Let's remove this. The vapor phase column here will disappear. When you just put it again, we start to make the vapor phase. What does this mean, Raja? The composition I entered to the simulation, to the HYSYS software, he start to extract from his library the phase envelope for the methane, the phase envelope for the ethane, the phase envelope for the propan and the butane, and all the components I listed on the composition. And he start to make the equilibrium constants for each component on the list. Why? To make the constant for each component multiplied by the mole fraction of each component to generate the phase envelope for the mixture. Which will be the basis for every calculation coming upward. When I tell him that the pressure is almost 250 psi G, he automatically jumped to the phase envelope, calculating that there will be a vapor phase and the pressure is almost 17.24. He now making the phase calculation. He have a vapor phase and this bar G. Just now we will enter the amount of liquid or amount of gases we are receiving from this well. Back to the base of design, page 22, case 1 for me. The gas flow rate is 20 million standard cubic feet. Million standard cubic feet. Million standard cubic feet per day. Here I just press 20, then I select the unit. Now we have the gas phase from the mixture. We have the gas phase from the mixture. You got me? Hello? Anyone following me?
Yeah, okay.
Let's name it gas. Let's make another stream for water. The temperature will be the same as we said, 50. The pressure will be the same. It's coming from the same reservoir. The flow rate, amount of water, according to page 22, amount of water is about almost 2,000 barrels per day. So here standard liquid will be 2,000 barrels per day. Here we are. Then the last one is the composition. It is almost all water. This is the water stream. Now we have the gas, we have the water streams coming to our side from the well. We have the last stream, which is the condensate. Temperature the same 50, pressure the same pressure. And the flow rate from page 22, the condensate flow rate in the case of 250 is almost 1,000 barrel condensate. Barrel per day. The composition will go to the page 20, and we will take all the heavy components to put it in hexane. Let's say for the hexane here it is almost 0.8, and here 0.1, and here 0.1. Okay. Did you see here he add liquid phase, he didn't add a gas phase. When we enter the water, he add aqueous phase. When you enter the gas, he add a vapor phase. This is the three which is coming from the well. They are coming all mixing in a pipeline, right? Here's the gas, here's the water, here's the condensate. Then we have the mixture out. Here's your mean feed. That's what's coming from the pipeline entering your plant. Normally in petrochemicals, you got this stream from any gas plant beside you. Normally for any gas plant, you got all of this. Normally for any oil plant, you got only 2 mixtures or 3, depend on the type of the reservoir. Oil and the water, oil, gas and the water, depending on the reservoir type. The stream here, Naja, please, can you tell me what was your first equipment on the PFD? Naja? Okay, Raja?
Is it visible on the screen, the PFD, the slices, all the guys?
The PFD, which is the second file I send it to the WhatsApp.
Now yes. Okay.
Open it. Tell me the first equipment. What is the first equipment?
The size, I'm not able to see the flow sheet. It's only blank.
Sorry?
The blank. For me, it's black on the screen. I cannot see the flow sheet. The screen background, can you change to white or something like that?
Is it the same program with everyone?
Yes, yeah. We have the compression station unit, the PFD for it. So
what's compression station? The process flow diagram, I open it now, it is very clear for me. I don't get it, what you are suffering. Okay, 1 minute. I have another problem. I'm sorry for this. Now it is a picture. Is it clear now? I don't understand any word. Is it clear now or no?
Yeah, it's clear, but we are not quite sure if it is the same PFD you are talking about, because you in the simulation software, so you mentioned the just like the flow line which comes from wellhead, which should feed the plant, right? But here we have something for compression unit or something like this. So is it the same PFD you are talking about, or?
Yes, it is the same. Normally you receive one line from the well, right?
Yeah.
Here is the line. Here is the line. Let's write it from the gas well. Here's the pipeline. You enter your plant. Just ignore all of this. You have any problem? Hello?
Yes, please.
Here is the pipeline. This is how looking. What? Why?
Yeah, this is what we are talking about. It's the same for me as well.
Hi, for me, nothing is visible. Only I am able to see a black screen.
How come? Now? What you see now?
I can see black screen, the high screen.
Yeah, the same.
The same?
Yes, yeah.
Okay.
Maybe it is the same thing or coloring this.
Oh. Okay, let me close it and open it again. Is it the same black now?
No, it's slight blue screen.
And you see inside?
When black is coming, maybe your view settings, you need to change view settings. Background. On the top of view, there's a view on the top. Yeah, let us see.
It's the first time to have this with me.
Yes. What is it?
What is the phone? I don't know what's happening here actually. You see in the WhatsApp what I'm trying to make?
Yeah, it just appeared and disappeared. Yeah. Yeah, yeah. It's just like popping out from time to time.
First time to have this, wallahi. It's the same black, right?
Yeah.
Yeah.
When you go to home, it is appearing. Go to home, you are doing something.
Auto what?
From home, when you went to home, it turned into white. Yeah, here, when you are doing something. It is
What I should do from home? I don't get it.